This next section deals with correlation coefficients, and how to interpret correlation coefficients. So we'll start with understanding what it means by having a correlation coefficient. Correlations are also referred to as Pearson's R or a bivariate correlation. In essence, it's a number that can go from -1 to +1 and all sort of gradations in between by tenths and hundredths. And a positive correlation is usually as a positive number, and it means that as one variable goes up, the other variable goes up. If it's a negative correlation, as one variable goes up, another variable goes down. So we talk about direction. So direction is either positive or negative. And then there's magnitude. A high positive correlation is something that approaches 1. A high negative correlation is something that approaches -1. And so really what we're talking about is how two variables vary together. They're not necessarily related. They may be, but they aren't necessarily, because just because things are correlated doesn't mean that one causes the other, that they're directly connected. So a correlation of 0 means that there is no relationship whatsoever between the two variables. A value of +1 means that there's a perfect linear relationship where everything falls on a line, and as one measure goes up, the other measure goes up incrementally, and exactly the same. And then a negative number means as one goes up, one goes down. And so again, a perfect negative correlation means for every 1 unit it goes up, 1 unit goes down. And of course, those extremes are rare. Zeros are very common in terms of correlations, but the very big extremes of +1 or -1 are rare. So typically we'll see things that are lower than that and variations on that. And it's not enough to just look at the magnitude and the direction of the correlation. We have to think about statistical significance, which we will get into in a little bit. Visually representing data is very important, and so graphs are a great way to show the relationship between two variables. So the one on the left below is really a very small correlation, a very low correlation. In essence, there's very little relationship there at a 0.05. And so that means as one variable goes up, maybe another variable will go up at the same time. On the right, however, we see a perfect correlation, right? Again, remember, these don't really exist in real life, the perfect correlations, but just gives you an idea visually what that looks like. So everything falls specifically on the line, and it goes from lower to higher perfectly in terms of increments. What you would more likely to see is some variation. You'll see a pattern, but you'll see variations, some higher, some lower. Nothing will land specifically on the line if we're graphing things, and we'll see that in some other pages here. But this is a good visual of what the perfect world would look like. But the bottom line is we don't normally see perfect correlations of 1.0 like that. So on this page, we see a scatter plot that is much more representative of the types of things that we will see. Because remember that selection and correlations among variables when we're doing selection is not a perfect art. You're never going to see a perfect correlation or a perfect validity coefficient, because there's a lot of factors that go in to predict job performance. But this is a great example of a moderate correlation, 0.43. It's mid-range. And of course, we would need to know the sample size that we used, and we would need to know how statistically significant the results are. But generally speaking, a correlation of 0.43 gives you a good sense of, a negative 0.43, sorry, shows you that it's a negative relationship. And if you create that line of best fit, as you can see there on the graph, it goes from around 4 in terms of performance, and then scales down to 10 in terms of test scores. And so what you'll see is for lower test scores, there's higher performance, and then for higher test scores, there's lower performance. So would this be a good, useful tool for making hiring decisions? Well, I mean, the bottom line is if people score well on a test but do poorly on the job, then it could be a real moderate predictor, but we would have to interpret in the opposite direction. But my guess would be on this one in particular, no, we wouldn't want to use this. We want things to have a positive correlation. The higher the score, the better performance they would do. Unless you're testing for negative skills, right? So if someone has a lot of negative skills, yeah, they're going to perform poorly on the job. So it really kind of depends on what the test is testing. If it's testing positive skills, things that we want on the job, then we don't want to use a test like this. But if the test is testing for negative things, if you're, the likelihood that you indicate these negative attributes, then we would be more likely to see lower performance with higher scores. The more negative attributes you have, the lower your performance would be on the job. But generally speaking, when we're testing for something, we're typically testing for the affirmative, not for the negative. So we typically wouldn't want to use a test like this if we were testing for positive attributes in individuals. This slide represents a correlation that's actually relatively low, but it actually is a really good example of a curvilinear relationship. And what we mean by that is, even if it's not a linear relationship, it does represent a curvilinear relationship, so that high scores and low scores are not good, but you want scores that are sort of in the middle. And one way you can think about this is stress or tension or conflict and performance. On the x-axis, the higher the stress or the higher the conflict, the lower the performance, and then the lower the stress, the lower performance, but mid-range is better in that context. Here is a different way of visually representing a correlation besides the line graphs as we were talking about. These are Venn diagrams, and it shows when there's overlap between one variable and another variable, this is the extent to which there's overlap between the two variables. Gives you a good sense of whether or not something is highly correlated. So this is a great visual for a highly correlated relationship between two variables. So in the previous slide, we had an illustration of two very highly correlated variables that had a lot of overlap. This is the exact opposite of that. These are two variables that have no relationship whatsoever. They don't overlap at all. So it just gives you a sort of a visual idea with this one that they are not correlated at all. So therefore you wouldn't see any overlap. On this slide, you see a moderate to strong correlation between two variables. There's enough overlap between the two variables that we have a pretty good idea that as one variable goes up, the other variable goes up, or as one variable goes up, the other variable goes down. Remember, this doesn't address directionality at all because this doesn't reflect a negative or positive. This just reflects the magnitude of the overlap, the magnitude of the correlation, whether it's positive or negative. So in this situation, X and Y are moderately correlated. This is probably about a 0.4, 0.5 correlation, which is pretty strong in the realm of selection tools. So in what way do we use correlation coefficients? And one of the ways we can do that is just looking at the relationship between two variables that are really important to us. So we may look at store size and how much staffing we need for that store. So we may have some historical data and we want to look at how large the store was in terms of square footage or in terms of sales, and then we want to correlate that with historical information on how many employees we need to have to cover those square footage or cover that particular level of sales that we're looking for. And then once we see that correlation, we can then make some predictions about future store size or future sales and what we will need in terms of staffing levels. So we want to make sure that our store size, whether it's square footage or number of dollars worth of sales, is in relationship with our staffing levels, that those things should be in alignment. Another thing we might look at is how senior somebody is in the firm and how good of a performer they are, particularly if we care a lot about seniority systems, bona fide seniority systems. We want to have evidence that the more senior workers are higher performers, they're better achievers, they are contributing more to the bottom line of the company. So if we are debating whether or not seniority, a bona fide seniority system is something that we want to implement in our company, having that correlation would be really helpful. Other things that we might want to look at is the time to fill a job with the higher quality. So what we mean is, does it take us longer to find a higher quality hire? And what is sort of the approximate amount of time that will take for us to get a good quality hire? How long is it going to take us to get that person? And so if it's the longer amount of time, the higher quality, that could be problematic for us, because then that's basically telling us the longer we look, the more likely we are to find a high quality candidate. And I don't think that that's true. I suspect if you go back a couple slides and remember that curvilinear relationship, that may be more close to what we're looking for. Even though it doesn't have a high linear correlation, the curvilinear relationship is much more relevant to what we're trying to talk about. For example, short periods of time, really short, you're not going to get good quality candidates, right? You're just going to get somebody really quick to fill a gap, and you're not going to be picky. And if you take a really, really long time, that's also problematic, and you might satisfice if it takes you a really, really long time. But maybe there's a sweet spot somewhere in that middle where you're going to get the best quality candidate given a certain amount of time that you're looking. And so it is important to not just assume every relationship is linear, that it might have a curvilinear relationship. So even though it might have a low correlation, if you actually graph the data, you might see something very different. The last one for an example that they give here is the quality of new hires with business performance and satisfaction. So we might have an objective measure of the quality of our new hire, and then we're going to correlate that with business performance and satisfaction, in the next few years. And so we might want to be tracking whether or not the quality of the hires that we brought in was going to be related to our business performance or satisfaction. So there's a lot of different ways to think about correlations and the way to use them. In the simulation that you guys did in Management 430, you should have been thinking about the relationship between certain programs that you implemented and the outcomes, the metrics that mattered to you. So, as I put more money into training, did I see productivity go up? As I put more money into quality management, did I see morale go up? As turnover went up, did morale go down? So again, looking at those correlations. And those are the things that you want to be thinking about when you're trying to do good analyses to make your case to financially support a particular program. And that's the goal of HR, is to say, here's some data, this supports that we should put more money into these programs because here's some correlations that matter. When we are interpreting correlations, there's a couple things that we need to think about. And here on this first page, we have to consider sampling error. When you, as it says here, when you're using statistics, including correlations to draw inferences or conclusions, you have to recognize is that you don't know whether or not your sample is representative of the whole population or the whole range of scores. And so if you're concerned that you may not have a representative sample, you use statistical significance to try to give you more confidence that the correlation that you're seeing is representative of your population, or at least represents the probability of seeing something within the larger scope of your population in your sample. And so we'll see in the second slide about how that actually works. So getting back to this idea of what is statistical significance. Statistical significance is the degree to which the relationship that you're observing, the correlation that you're observing, is unlikely a sampling error, that it actually gives you confidence that this is something that actually exists and it's a meaningful relationship that is observable, and it's something that we need to pay attention to. So if you want to have a good, strong correlation between two variables, it's not just the direction and the magnitude, it's also about the statistical significance. It depends on the size of the sample that you're using, and then you want to see whether or not the relationship that you've observed actually exists and isn't just a random sampling error. Okay, practical significance is really about the the impact that it has on your significance. For example, with large samples, a small correlation is statistically significant, but the relationship may not be strong enough to justify the expense and time of using the predictor. So with a large sample, even if you have a statistically significant correlation, it's going to be statistically significant because the sample is so big. So with a smaller sample, you're more likely to see that. So you might be better off with something that has a low cost to you that you can use it, and it might be a significant correlation, statistically significant correlation, but it doesn't cost you a lot. So it's okay if there's some errors in that context. If an assessment that's correlated 0.15 with job success is expensive, it's really not useful for us. So doesn't have practical significance. So our goal is, if it's something is inexpensive and it has a significant correlation, but that correlation is smaller, we're better off using it if it's inexpensive. But once it's expensive and time consuming, you're not getting a lot of bang for your buck. It's sort of the utility of your instrument is not going to give you a lot. So our goal in practical significance is keeping in mind how large the sample is. If it's a large sample, recognize that small correlations are going to be significant. And if you're using a large sample and it's significant, as long as it's a low-cost instrument, you're fine. If it's a high-cost, high-maintenance instrument, then you probably want to stay away from that.